Hello, here is the final from fall 2018 for MA265. We're going to run through all of the questions that we know how to answer with our midterm 1 material. And let's get going. Let's consider this system of linear equations. For what value A is the system inconsistent? So right off the bat, let's put this into matrix form. We have 1, 2, 3, 1, 3, 5, 4A, 2, 3a squared, 0. And really, my goal is going to be to get this whole row into the form, or at least one row into a form where we have a situation where a is the only determining factor that decides whether or not the system is consistent or not. So we're going to start simplifying. I'm going to subtract 3 row 1s from row 2 and 2 row 1s from row 3. So we have 1, 2, 3, 1, 0, -1, -5, a minus 3, and 0, -1, let's see, minus 6a squared minus 6, and minus 2. And we're actually almost done because we can subtract row 2 from row 3, and we will get 1, 2, 3, 1, 0, -1, -5, a minus 3, 0, 0, a squared minus 1, and 1 minus a. And we see that if we plug in a equals -1, this last row will become 0, 0, -1 squared plus 1 is 0, and 1 minus -1 is 2. And this is inconsistent right here. This is saying 0 x1 plus 0 x2 plus 0 x3 is equal to 2, which doesn't make sense. And A is our correct answer choice up here. All of these other ones, you will get non-zero values in this spot, and it can be a zero value in this spot, but as long as we don't get that 0 equals 1 kind of identity, we're good. So A is our correct answer for question 1. Question 2, consider the equation AX equals B, where A is a 3 by 2 matrix and B is in R3. Which of the following statements is true for every matrix A? So let's take a look at what form A is going to be in. It'll have 3 rows. So I'll just make an example matrix here, 1, 0, 0, 0, 1, 0. And remember that we can think about these as the place in, so our output's in R3. You can see that with the 3 columns. Our input space is in R2. It's saying, where are we putting the basis vectors from R2? Where are we transforming those into R3? So our basis vectors in R2 are going to be 1, 0 and 0, 1. That's the basis for how our coordinates are measured. But what this transformation here is doing is absolutely nothing. It's just taking the xy plane in 2 dimensions and putting it exactly where it was before. The 1, 0 basis vector is landing on 1, 0 with a z coordinate of 0, and the second basis vector is landing on 0, 1 with a z coordinate of 0. So hopefully you can kind of visualize that we've got this 2-dimensional space, and we're kind of expanding our view to be looking at 3D space, but the plane itself is not changed. So we can start with this example. We can kind of start going through some of these options. The equation AX equals B is inconsistent for every B in R cubed. Well, that's not true. We just said that this matrix right here does absolutely nothing to the consistency or inconsistency of our system. Sure, there are going to be some values if we kind of draw this out. If you choose any, and there's our plane extending all along there, if you choose some vector up here, obviously we're going to be inconsistent, but there are also values here where we are consistent if we stay in the plane. So A is incorrect. We don't have to be inconsistent all the time. whenever ax equals b is consistent, it has exactly one solution x. Well, this is also not true. We can go take a look at our transformation matrix and change it a little bit. If we make this a 0, this is saying stick everything on the same x coordinate that it was in 2D space, put it at that same x coordinate in 3D space, but take all of the y coordinates and compress them onto the x-axis. So this, if we draw this out, x, y, z, every y coordinate is now all along this line the line along the x-axis, y equals 0 and z equals 0. So you can see we've compressed infinitely many points onto this one point on the line. So no, we don't have to have exactly one solution x. And like we saw earlier, we don't have to have infinitely many solutions x. Our matrix that looked like this right here was 1-to-1, and it did absolutely nothing to 2D space. It just expanded into 3D space, and we had one solution for every input vector. So C is incorrect. What about D? Okay, we're inconsistent for at least one B in R cubed. Well, this, as it turns out, is true because if we take two vectors in 3D, this is in 2D space, but hopefully you can think of these in 3D space a little bit. If you think about two vectors in 3D space, the area spanned, or their span, is going to be the plane that they both lie in. And there is no way to span all of R3 with only two vectors. So no matter what, our span is either going to be a single point, a line, or the plane span between two of these guys, two vectors, but there's no way for us to span all of R3, so D is, correct, will always be inconsistent for some B. And then E, if the columns of A are scalar multiples of each other, then the equation has one solution. Well, no, if they're scalar multiples of each other, for example, if we had these guys right here, what would this do? Well, it would take all of the x, it would take the x basis vector, and I'll draw this one out again, x, y, z. It will take all the x basis vectors and put them in the same spot, but it'll take all of the y basis vectors, sorry, there aren't multiple, there's just one, the y basis vector, and it'll put it along the same line. So that is going to give us this infinite line. And so you can hopefully see how, we're taking 2D space, we're compressing it into one dimension, so we're going to have infinitely many solutions instead of only one. So there we go, D is correct. Skipping eigenvectors. Not doing that yet. Okay, question 4. Which of the following subsets of R3 is linearly independent? We can do this one real quick, given the stuff that we talked about last time. We are looking for columns that are multiples of each other. First off, I see that B, those two are multiples of each other. And there are only we're not trying to span R3. We're just looking for linear independence. Yeah, so these guys are multiples of each other, so that's no good. Also, A, 0, 0, 0 is always a linear multiple, or a linear combination of any other non-zero or zero vector, actually. So A is also out. Now going through these other ones, if you have a row of all zeros, we are also going to be linearly dependent. So rows of zeros and columns of zeros are no good. Now let's take a look at these other two. We have 1, 4, 2, 2, 5, 1, 3, 6, 0. Let's try to put this into row echelon form. We have 1, 4, 2. I'm subtracting row 1 from row 2 twice. 0, -3, -3, so we can change this to 1, 1. And we get 0, -6, -6. And that will turn into 1, 1. And so you see, using row 2, we can make row 3 a row of zeros. And we know that a row of zeros is no good. We would want to have a pivot in that row in order for us to be linearly independent. So D is not correct. And if we've done everything correctly, 0, 1, 4, 1, 2, negative 1, 5, 8, 0. This should be linearly independent. I'm going to switch these two rows around. Let's see, subtract 5 row 1s from row 2. We will get 0, negative 2, 5, and let's see, I'll add 2 row 2s. That'll give us 0 and 13. And so you can see we have a pivot position in every row. Each one of these columns has some degree of freedom that the other ones do not have. There's no way to make a non-zero value here from the other entries in the third column, just like that holds for these other two. And so E is our correct choice because its entries are all linearly independent. Okay, 5. We are given A transpose, and we're trying to find the 3-1 entry of A transpose A. So A transpose is 0, 1, 2, 3. Whoops. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then A is just the transpose of A transpose. So we can set that up as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we know, since we're multiplying rows on this side and columns on this side, we're going to get the 3-1 entry of A transpose, A transpose A. We're going to get that by multiplying the third column of this, the first matrix we're multiplying, by this first row of the second matrix that we're multiplying. And that will give us 0 plus 9 plus 20 plus 33, which is, let's see, 20, 33, 9, 2, 7. Nope, 6. Sorry about that. The pressure's real. So E is our correct answer for 5. Okay, just checking the other ones I forgot to. Question 6, we're finding A basis for the null space of A. So the null space is just going to be the solutions to AX equals 0, or the augmented matrix negative 3, 6, negative 1, negative 4, 0, 1, negative 2, 2, 3, 0, 2, negative 4, 5, 7, 0. And it's a bad habit for me, but I'm going to copy the entire thing to save some time and start working on it. I'm going to add 2 row 2s to row 1. That will make this guy 0. Oh, sorry, when I said 2, I meant 3. 3, so that's going to be, plus 6, so 5, plus 9, so 5. We can simplify that down to 1, 1. We can subtract here 0, 1, subtracting 2 row 1s. Let's see, we can subtract here and get 0, 2, and we can take row 1 and subtract, we can take row 3 and subtract from it 2 row 2s, and we will get 0, 0, 0. And so we see if we rearrange everything that we've got over here carefully, we see that x1 has a pivot, x3 has a pivot, but x2, x4, and x5, there is no x5. We set this equal to 0 as a homogeneous system. So x2 and x4 do not have solutions, and we can set up these solutions with this equation. So this will be x1 equals 2x2 minus x4, and x3 is equal to negative x4. And we can put this into a nice little vector equation. X2, well, how is it dependent on x1? Well, x1 is equal to 2x2, x2 is equal to 1x2, x3 is not dependent on x2, and x4 is not dependent on x2, and then x4, our other, yes, our other free variable x4, x1 is equal to -1 x4, x2 is equal to 0 x4, x3 is equal to -1, and then x4 is equal to 1 x4. And so if we have done everything correctly, we should have, okay, I thought we had an issue for a second there, but taking a look at option C, we'll see that if we, change the sign of every component in our x4, we get C, and that vector is just in the opposite direction. And since that we're taking all the linear combinations of that vector, we're actually looking at the same line there. And I'm not sure if I did some row operation errors. If you can find them, please let me know. That would be really cool. But other than that, we did get an answer that was equivalent to option C, which is the correct answer up there. Yeah, so I vaguely know how to do these. Pretty much you're trying to put it all into upper triangular form and multiply the main diagonal altogether. But so far in all of my run-throughs, I've never gotten this question right. I always get the inverse, like I get -180 instead of 180, or the other way around, I'm not sure. But right now, I'm not doing a 6 by 6 determinant. Oh, it's only 5 by 5. It's still really scary though. Okay. Question 8 uses a lot of the same principles, though. So we are told that the determinant of this guy is -16. So what is the determinant of this guy right here? So first of all, we see that a row has been multiplied by 2, where this top row up here has all been multiplied by 2. That multiplies our determinant. By 2. So if the determinant of this is -16, we know that we're going to have to multiply that. Let's see, -16. We know that we're going to have to multiply that by 1/2, and we can go cross off that change in there. Okay, let's see. We know that adding rows to other rows, even multiples of those rows to other rows, does absolutely nothing. So this plus 6c1 minus 6c2 plus 6c3 does nothing to our determinant, so we can completely ignore those. Okay, what else have they done here? Well, they have transposed the matrix, and we know that a matrix transpose, the determinant is the same thing as the matrix if you didn't transpose it. So let's transpose this one back. We have -b1, b2, oops, sorry, that's wrong order. We have C1, -C2, C3. We have A1, -A2, A3. And we have -B1, B2, that's a weird B, B3. Okay, we see that 2 rows have been negated. So they've been multiplied by -1. And so if we get rid of all of those changes, we are essentially multiplying by -1 twice, which is the same thing as not doing anything. Okay, so we're getting there. It's good to also notice that we're going to need to switch some rows around. We'll need to switch the positions of A and C, and then afterwards we'll need to switch C with B. And after those 2 changes, we'll be left with A1, A2, A3, B1, B2, B3, C1, C2, C3, which is this matrix right here. And we know that flipping 2 rows, all that does is multiplies our determinant by -1, and we've done that twice. So again, we're multiplying by -1 twice, and so our answer here should be E, -8 for question 8. Perfect, which is correct. 9, let's find the 1, 2 entry of A inverse. So I use cofactors for this. I I learned it from a YouTube video like a couple weeks ago, and it works pretty well for me. So the 1, 2 entry is going to be this guy, and we know that the last step in taking the inverse of a 3x3 matrix using the cofactor approach involves flipping or changing the positions of everything right down the central diagonal here. So we are going to be finding the determinant of the matrix, so 1 over determinant of A, and we're going to be multiplying it by the cofactor of that position, which is going to be, and I kind of encourage you guys to go, look at some videos for this if this is confusing, because it's definitely confusing. I still forget steps every once in a while, and I'm not the best at explaining exactly what's going on. But the cofactor for this thing is just going to be the determinant of the matrix that is not in the row. Wait, I did that wrong. There we go. That is not in the row or column that our position here is in. So we are left with 5, 8, 4, 5. And we also know that all of these cofactors are going to have different signs. So we're using a plus, minus, plus, minus, plus, minus, plus, minus, plus kind of scheme. And since we're looking at this position, it's going to have a sign of -1. So the determinant of this is going to be 25 minus 32. 25 minus 32 is -7. But since we have a sign of -1, all of this is just going to turn into 7. And so we're left with 7 over the determinant of A. The determinant of A is going to be 3 times this submatrix minus 5 times this submatrix plus 8 times that submatrix. So let's do that. 3 times -2, 5, 4, -9 plus, minus times 5 multiplied by the determinant of -2, 5, 2, -9. And then to that we're adding 8 times -2, -2, 2, 4. Ooh, sounds like someone's moving furniture. Okay, so let's solve all of these. So we have -10 plus 36 is going to give us, 26 in here. Oops. Minus 5 times -10 plus 18, so 8. And we'll just replace that with 40. And then over here we have -8 plus 4, or just -4. So this is minus 32, or minus 72. Okay, we're almost there. So 26 times 3 is going to give us 78. Minus 72 is 6. So our answer should be C, 7 over 6, and that's extremely satisfying. That is our correct answer. Number 10, which of the following sets of vectors x, y, z are subspaces of R3? So we're going to be doing a lot of visualization. It might give you some flashbacks to Calc 3, and I'm sorry if I bring back some bad memories, but here we go. Okay, so we have the set of vectors satisfying the condition x, y, z equals 0. Well, we know that to be a subspace, we have to be closed under scalar multiplication and vector addition, and we also have to include the 0 vector. Well, this clearly does include the 0 vector. In fact, this guy, all obviously include the 0 vector, because we can just choose 0 for x, y, and z, and then we are at that 0 position. But if we actually think about what the graph of x, y, z looks like, it's just going to be any point where one of our 3 coordinates is 0. So this will be the 3 coordinate planes here, and nothing in between. And importantly, if we take a vector, say in the, let's say this is the xz plane, and we take a vector in the xy plane and we add them together, we'll get something poking up into space in between, which you can kind of visualize as coming up out of the page, kind of angled towards you, which is clearly not in the set, so we are not closed under vector addition, although we are closed under scalar multiplication. Okay, number 2, we have the set of all vectors satisfying that condition. So this is a plane, and it's set equal to 0. So we know that we pass through the origin, which is great. And just knowing how span works can actually help you solve this one, because we know that anything that can be represented as a span is a subspace, because a span is defined by the characteristic that you can take the elements that form that span and choose different linear combinations of them, which involves being closed under scalar addition and scalar multiplication and vector addition. And so this plane here, take any two elements on the plane, add them or multiply them, do whatever you want, you cannot get off that plane. So 2 is correct. Okay, what about number 3, the set of all vectors satisfying that condition there? Well, that's just going to be a sphere of radius 0. If you take any vector satisfying those conditions, the only one you have to choose from is the 0 vector. And if we have the 0 vector and we multiply it by any scalar multiple or add it to any other 0 vector, we're always going to stay within the set. And that 0 vector is our origin. So 3 is all good. What about 4, the set of all vectors satisfying this condition here? Well, this plane is great for the fact that it's a plane, and that if you take any two elements of the plane, you can multiply them by any non-zero constant or add them together, and you'll stay within the plane. But we do not include the origin, so if you multiply any of those elements by 0, you will pop out of the plane back onto the origin. And remember, this plane will cut through the first octant at 1, 1, 1, and we obviously do not include that origin there, and so 4 is no good. What about 5, the set of all vectors satisfying the condition x equals y? Well, that's a line that passes through the origin. If you take any point on that line, add it to another vector to a point on that line, you'll stay in that line. And also, if you multiply by any scalar multiple, this thing doesn't care. It goes on on to infinity, and so it is also a subspace of R3, and so our answer is C. Okay, good. 11. So we have A with 5 column vectors, v1 through 5, and it's a 4 by 5 matrix. So we're told that v1 is a linear combination of v1 and v2, and v4 is also a linear combination of v1 and v2. So what that means is that we have 2 vectors, 2 columns, let's see, v3 and v4, that are redundant in our span. And so we can take a look here and see that at most we will have 3 pivot positions, because at most these three rows can be linearly independent of each other. So rank has to be less than or equal to 3. And since we know that our matrix has 5 columns, the nullity will have to be greater than or equal to 2, and you can kind of correspond the nullity with the number of linearly dependent columns of this vector, not this vector, but this matrix A. And we remember that the rank plus the nullity has to be equal to the number of columns, which in this case is 5. And let's say if rank is actually 2, nullity will have to be 3 to compensate. So A is correct. And just to remind people, the rank is the dimension of the column space, and nullity is the dimension of the null space, which is the solution to AX equals 0. And okay, let's go check. Yep, we're good. Okay, you didn't see that. Okay, question 12. Which of the following sets of vectors is linearly independent? So we're looking for two vectors, or sorry, linearly dependent. We're looking for two vectors, or three matrices, or things in the polynomial space that can be formed from a linear multiple of each other. So taking a look at option A, well, these guys are linearly independent. If we're just in R2, we're looking to see if there's a multiple of this guy that will give us this guy, and there isn't. There's no way to multiply the first by a scalar multiple and get the second. So those guys are linearly independent. And I'm actually going to save a little bit of time here. You can go and prove that these guys are linearly independent by showing that there are three pivot positions in each one. But if we skim our way down to D, we'll notice that if we take 3 times 1, 1, 0, 0 and add 3 halves times 0, 2, 2, 0, we are going to get 3, 3, 3, 3. So these guys are linearly dependent. And as far as it goes in this point in my linear algebra class, we have not done this yet. So by the time the final comes up, we'll be talking about, you know, the polynomial vector space or whatever. But right now, I don't really know what's going on with those. I can try, but you know, don't feel like it. 12D, and that's correct. And I think finally, finally, we're going to take a look at 14. We have a linear transformation whose standard matrix is given there, and we are given some things to think about. So first off, we know that this vector is taking in 4D space and spitting out vectors in 3D space. So there's no way that this matrix can be R3 onto R4. If anything, it's R4 onto R3. And we would know if it's R4 onto R3 if its columns spanned R3, which we know that they do because we see that it has 3 pivot positions. So it does map R4 onto R3, which means that it is an onto transformation, but is it 1-to-1? Well, it's not 1-to-1 because 1-to-1 means that the transformation is linearly independent. Well, I shouldn't say the transformation is, I should say that the columns of A are linear. I didn't plan this very well. Linearly, columns of A are linearly independent. And since we have 4 columns in 3D space, if we have 3 linearly independent columns in 3D space, we are going to span all of R3. There's nowhere to put a 4th column where it will not already be in the span of the first 3. And so it is not 1-to-1. So 2 and 3 are correct. So D is our correct answer for 14. Okay, awesome. I don't know. Thanks for tuning in.